Hi, this is David Van Vranken here at UC Irvine. This is lecture 14, Chemistry 51C. And during the past few days, I've seen lots of news articles come out about a potential therapy for coronavirus called remdesivir. This is a compound that was made by Gilead Sciences, I don't know how many years ago, as a potential treatment for Ebola virus. And of course, when the coronavirus COVID-2 came out, lots of companies were throwing all different kinds of compounds at these RNA viruses to try to figure out if there was something already existing that could be used as a treatment. And recently, remdesivir has been shown to have a little bit of activity against coronavirus. And so let's talk about this remdesivir compound. It's an interesting compound. It's an inhibitor of the SARS-CoV-2 RNA-dependent RNA polymerase. That's this protein right here that's encoded by the RNA genome of coronavirus 2. And what struck me about this molecule is not necessarily the biological activity or the target, but the active metabolite of remdesivir is this derivative that looks a little bit like a nucleotide, a component of RNA. It binds to the active site of this RNA polymerase. And whenever I see molecules that are based on ribosyl derivatives like this one, it just brings back incredible memories for me. And so let me take you back about 30 years to my time as an undergraduate researcher at the University of Texas at Austin. The first lab that I worked in doing organic synthesis, whenever I see ribosyl derivatives, it reminds me of the first reaction that I ever ran in an organic chemistry laboratory, in a research laboratory. And so let's go ahead and talk about that reaction. I think it's like remembering your first kiss. I think every synthetic organic chemist out there remembers their first reaction. Let's talk about that. First reaction that I ran in a research laboratory doing organic chemistry is very similar to chemistry that you already learned. You already learned that if you want to make acetals out of ketones or aldehydes, that it's very efficient when you use 1,2 diols, hydroxy groups, also called vicinal diols, where you have hydroxy groups on neighboring carbons, because the 5-membered rings you generate are exceptionally stable. The equilibrium lies towards that side. And the very first reaction that I ran in a synthetic laboratory was to take this ribose derivative, ribonolactone, which you can see has these 2 hydroxy groups on the same side of the 5-membered ring, just ready to form an acetal. And so I put this into acetone. I added a catalytic amount of hydrochloric acid, and there you go. I got an amazing yield of ribonolactone acetonide. That's the acetal derivative. I was hooked. At that point, I decided I wanted to become a professor in chemistry. And things seem to have worked out from there. So hope you're as excited about the first reaction you ever run in a research laboratory, if you choose to do research. And let's go ahead and talk about the subject for today's lecture, which is formation of esters and amides and reactions of acid chlorides. That's the cool stuff that we're going to be doing today. On Wednesday, we talked about 2 amazing reactions of acid chlorides. We talked about converting acid chlorides into esters in 1 step in high yield, using just by mixing in an alcohol and adding in a base, pyridine, to soak up HCl. And then I told you about a reaction for making amides. You take an acid chloride and an amine, and then we use the base triethylamine. We need a slightly stronger base when we're making amides because we want to soak up HCl, and amines are more likely to be protonated. They are more powerful bases than alcohols, so we have to use a stronger base. And we make amides in high yield, reliably, in a single step. Amazing chemistry. Let's go ahead and talk about the mechanism for those reactions, for forming esters and forming amides from acid chloride. I'm going to show you a mechanism here using dialkylamine as the nucleophile, but this mechanism also applies to alcohols or monoalkylamino groups. You just replace R2N with RO or RNH, and it's the same mechanism. And the mechanism starts with the addition of the nitrogen lone pair to the acid chloride. Acid chlorides are so reactive, way more reactive than aldehydes or ketones, and it's so easy for amines to just simply add in there. We don't substitute the chlorine in 1 step. That's insane. That would be an SN2 reaction, and that's not the way carbonyls work. You add to the carbonyl, and you push up the electrons to the carbonyl group. That's the way that type of chemistry works. So let's go ahead and draw out the intermediate for that reaction. We're going to have this methyl group up here. When you push the electrons up to the oxygen, there we are, we've got that O- sticking down there. And there's the chloride. Just be patient with that. That's going to act as the leaving group eventually, but not yet, because we first have some business here with this ammonium group. That nitrogen now has a positive charge. I'll just write the R2 like that. So before we can push out that leaving group, that chloride leaving group, using this oxygen lone pair, we have to get rid of this positive charge. It doesn't matter whether we've attacked with an oxygen alcohol, whether we've attacked with an amine, we've got to deprotonate that before we can push out that, that chloride leaving group. So this is where it's important for us to have some sort of a basic species. It doesn't have to be that basic, pyridine. And we're not going to specify, or triethylamine in this case, we're not going to specify what that base is because we're doing an arrow pushing reaction. We just want to acknowledge that the conditions are basic. In that case, we use the symbol B. Or if the conditions were acidic, we would use A-, the conjugate base from the acid, as our symbol. And we just want to show this symbolic base to do this deprotonation reaction. And that removes that positive charge from the ammonium group. So now we're ready to kick out the chloride. Let me go ahead and draw this next intermediate out. Also a tetrahedral intermediate. There we go. There's that alkoxide species sitting there. That's supposed to be R2 right there. And here's our chloride leaving group. If you thought chloride was a good leaving group for making carbocations, it's a way better leaving group when it's getting pushed out by some kind of a lone pair that's right next door. If this were a carbanion or a nitrogen lone pair or an alkoxide type lone pair, it's so easy to push that leaving group out. Let's go ahead and make that leave. Wow, that just feels great. This collapse of a tetrahedral intermediate. We're not making a carbocation with only 6 electrons. We're making a carbonyl group, and carbonyl groups are great. So after we do this deprotonation, we're going to end up with our amide species. Here we go. And that's it. That's the mechanism for amide formation using, in this case, it would be triethylamine. And it would be the same mechanism if we had an alcohol attack. The alcohol would attack, we would deprotonate the oxonium ion if it was an alcohol attacking, and then we would kick out the chloride in the next step. So really an important mechanism for you to know because acid chlorides are so essential. And the byproduct of this reaction is not particularly important in this case. It would be the protonated, in this case, triethylammonium group with the chloride. But this is just an arrow pushing mechanism. We're not worried about the identity of that species B. That's why we use those symbols. Okay, the book shows you some extra reactions of acid chlorides. What are the important reactions of acid chlorides? Making esters and making amides. That's the important reactions of acid chlorides. And those turn out to be so important in organic chemistry. Oh, also Friedel-Crafts acylations, but we've already talked about that. So what are some other reactions you can do? Acid chlorides are so reactive. So let's go ahead and talk about another reaction that the book tells you about, but doesn't really have a synthetic point to it. The reason why this is an important reaction to know about is because it's a side reaction that occurs. So let me just paint a picture for you. Let's suppose you're trying to make a methyl ester from this acid chloride and use methanol, but your methanol is wet. That's frequently a problem. When you buy methanol, a bottle of methanol from a chemical supplier, it's always got water in there. We have very special procedures in our laboratory to get rid of water that contaminates methanol. It's not easy. You have to distill it off of magnesium methoxide generally in order to get that dry. So we want some way to make the methyl ester. If you've got water in there, you have to worry about the fact that you're going to generate as a byproduct the carboxylic acid, unfortunately. So you might be hoping to get a lot of this methyl ester. And I'll just put that under in parentheses. But if you've got water in there, you're going to get a lot of, even more of, this carboxylic acid. Nobody really wants to get carboxylic acids. Why is that? Because you make the acid chloride from carboxylic acids. That's the only way to get the acid chloride. If you just finish spending a day in the lab synthesizing and purifying the acid chloride from the carboxylic acid, the last thing in the world you want to do is hydrolyze it right back to the carboxylic acid. Nobody would do that on purpose. That would be insane. But it's a common side reaction. We are so careful in the laboratory to try to get rid of water, to run our reactions under nitrogen gas instead of wet atmosphere. The air you're breathing right now is full of water and oxygen. Those are the enemies to all organic reactions in the laboratory. A second reaction you can do with acid chlorides, because they are so reactive, is to add carboxylate anions to those. Let me go ahead and draw another representation of this carboxylate anion, just to try to acknowledge the fact that you can think of this instead of a sodium-oxygen bond. There's a strong covalent bond. Well, there's a strong bond there. But you can sometimes draw this or depict this as an ion pair, and it helps you to think about the fact that the O- has nucleophilic character on a carboxylate anion. So it won't be surprising to you that that can attack an acid chloride and end up forming a carbon-oxygen bond. And so when you take an acid chloride and a sodium carboxylate, it could be a potassium carboxylate or a lithium carboxylate or some carboxylate salt, you end up forming anhydrides. Acid chlorides are so general, you can form any kind of heteroatom bond with those. It's just so easy to do. Now, this doesn't really have, why would you want to make an anhydride? Anhydrides are used generally in the same way that you use acid chlorides. They're much more reactive than ketones, aldehydes, esters. And so generally it's very easy to form bonds with these. So let me give you an example. Let's suppose you wanted to make an amide using this, and we added aniline. That's aminobenzene. And remember, I told you the base that you need to use when you use amines is triethylamine. Don't use pyridine, that's for alcohols. So you use aniline here and triethylamine, you're going to get an amide out of that. Let me go ahead and draw that amide functional group. There's the carbon-nitrogen bond we just formed. So easy. Now the byproduct of this reaction is not in any way interesting, right? The byproduct of this reaction is the acetate. There's kind of a leaving group there, and the triethylamine is just in there to absorb the acetic acid that gets generated. So you'll have this triethylammonium salt. And we're going to have a whole chapter on amines and ammonium groups and this equilibrium and amines as bases. Nobody would do this in the laboratory. Nobody makes acetic anhydride by going into the laboratory and taking an acid chloride and adding a sodium carboxylate salt. It's just kind of a hypothetical situation to show how generally reactive acid chlorides are. The reason is the only thing that people do with anhydrides is they use them to make esters and amides. And if you're going to make an ester or an amide, why wouldn't you just do that directly from the acid chloride? That's what all chemists would do. There's no real point to making an anhydride just so you can make an ester or an amide. So that reaction really has no point here. But again, it just shows how flexible acid chlorides are and how many different things that we can do with those. Okay, so again, we don't purposely take anhydrides, right, and react them with water. That's simply a side reaction that occurs when you've got water as a contaminant in your reagents. And we're always worried about that. Is water contaminating our reagents? Let's go ahead and take a look at these anhydrides a little more carefully, because we do use anhydrides frequently in the laboratory. But the thing about anhydrides is we don't make those, we buy them. There's a few anhydrides that you can buy that are very inexpensive and very common. And so we use these all the time, but not a large number of them. Here's one common anhydride, acetic anhydride. Pennies for bucketfuls. It's so inexpensive. And so if you want to make and put an acetyl group on an alcohol or on an amide, acetic anhydride is a great reagent for that. I think they use that in the synthesis of heroin from morphine, for example, in illicit laboratories. Another common anhydride, and I think you might have seen this in the chapter on dienes and Diels-Alder reactions. Maleic anhydride is a super common anhydride. Right? It's easy to make it. It's got this 5-membered ring, but that double bond is super reactive in Diels-Alder reactions. It has this low-lying unoccupied molecular orbital that is just screaming hot for Diels-Alder reactions. As soon as I see that, I want to do a 4+2 Diels-Alder reaction to make a 6-membered ring. But that's not what this chapter is about. This chapter is about the reactivity of that anhydride functional group. So I guess the other thing I really want to do with this anhydride with maleic anhydride is to add an alcohol or an amine to that carbonyl and open up the ring to make an amide or an ester. Okay, the last common anhydride, every laboratory has these sitting on the shelf just because they're so common, is phthalic anhydride. Phthalic. You say it like there's no pH in there. So if you're confused about that, the stupid pH, just ignore that when you say the word phthalic anhydride. And that's got the same reactivity as maleic anhydride. The difference is it's not at all a Diels-Alder dienophile. There's no way you can do Diels-Alder with those double bonds in the benzene ring. So it's really the interesting part of this is just the anhydride functional groups and how easy it is to attack that and make esters or amides out of that. Let's go ahead and take a look at this anhydride chemistry. If we take an alcohol, and I'm taking this chiral cyclopentenyl compound and acetic anhydride, and it's an alcohol, so we're going to use pyridine as the solvent for this reaction. Notice we're not breaking any of the bonds, this carbon-oxygen bond. That would require some kind of SN2 or SN1 chemistry. Nobody would want to do that. But when you throw in an acyl chloride or acetic anhydride, it's so inexpensive and so common, then we're going to make an acetate ester out of that. So let's go ahead and practice drawing out that product. Here we go. This configuration of the alcohol, it's got the same configuration. It started off S configuration. It stays S configuration because we did not, I didn't mean to draw the H here. We did not break or form this carbon-oxygen bond. What we do is we make a new bond here to the, sorry, I didn't mean to make that a stereochemical bond. I just tried to cross out my hydrogen atom. We end up making this bond, this carbon-oxygen bond to the carbonyl group. So we don't change the stereochemistry here. And the other byproduct of this reaction that's not really at all interesting is this salt, the pyridinium acetate salt. There we go. As a byproduct in the reaction. You would wash that away with your water and throw it away. Nobody cares about that. What we care about in this case is making an ester from your valuable chiral alcohol. That's what that's for. So again, we've got some anhydrides. You know, anything you're doing here, you pretty much could have done here with an acid chloride. For these cyclic anhydrides, you can't quite get the acid chlorides as easily from those. So it's kind of cool that you can buy those and they're so inexpensive. But those are the common anhydrides that you'll see in organic chemistry. And again, it would be very unusual to see anybody make an anhydride from an acid chloride in the laboratory. All right, so let's go ahead and take a look at reactions of anhydrides and the mechanism for reaction. And I want to talk about first, why are anhydrides so reactive? Because if I compare an anhydride to an ester and the chemical reactivity, esters are just not that reactive. An ester is less reactive than a ketone. Less reactive, can I even fit this on here? Less reactive than a ketone. Why is that less reactive than a ketone? Isn't oxygen electronegative? We said already the important effect of oxygen is that it donates into to the carbonyl group. The lone pair on oxygen is donating into the carbonyl group. You can't stop that. It makes it very hard for another nucleophile to bounce in there and collide with that carbon atom with enough energy to make a bond to that carbon, because there's already a nucleophile, that lone pair, donating into that carbon. Now, when we look over at the anhydride, there's a lone pair on the oxygen in the middle, but it's kind of distracted. It's like half its time, or it spends equal amounts of time donating into the carbonyl on the left and to the carbonyl on the right. So it's almost like you're getting half as much of this donation effect of the lone pair. All the electronegativity effect of the oxygen is there, making both carbonyls reactive. But as far as resonance, the lone pair is not as strongly donating. It's half as strongly donating. And so because of that, it turns out that anhydrides are really reactive. So they're not as reactive as acid chlorides, but you use them in the same way. Let's go ahead and take a look at the mechanism for acylation of alcohols or amines. It would be the same mechanism. And the mechanism starts off with addition of the oxygen lone pairs to the carbonyl. Now, if you were trying to add to an ester or a ketone or an aldehyde, you'd have to protonate that carbonyl because OH is not a good nucleophile. But anhydrides are so reactive. They're reactive. Acid chlorides are reactive and anhydrides are reactive. So you don't have to protonate the oxygen atom of the carbonyl in order to get this oxygen to add. Let's go ahead and draw up the next intermediate for that process. So when we add, we're going to have that O- that we create when we push the electrons up to the oxygen. We're still going to have this other acetate group, this acetoxy group sitting there. And here's our nucleophilic alcohol that just added. It's got that positive charge on there. It's an oxonium ion. And we can't, I feel like I want to make that acetate leave, but we can't do that until we deprotonate this neighboring atom that has a positive charge. Doesn't matter whether that's an amine nitrogen or an ammonium or an oxonium, we've got to deprotonate that if we want to push out the leaving group. So let's go ahead and draw out the arrow pushing for deprotonation. Recall that we had bases in these reactions. In the case of alcohols, we had pyridine. But again, this is an arrow pushing mechanism. We're just going to use a symbolic B because the conditions are basic for deprotonation of that. We had a full equivalent of a base to these reactions. And so that allows us to pull the proton off, and then that positive charge on the oxonium ion is going to disappear. And so when we do that, we end up with this intermediate. Let me go ahead and draw it down here. There's that oxygen minus with its lone pair. And here's our alkoxy group that added, you know, we deprotonated first, or sorry, we deprotonated second. I feel like whenever people see alcohols or amines and I tell them I'm adding a base to the reaction, the immediate thought is, oh, I've got to use the base in the first step. I always use bases in the first step. Somebody told, no, you don't use the base in the first step. You wait until the alcohol adds. For some reason, I find that people automatically think that if the conditions are basic, you always deprotonate first. And maybe that was true way like 8 months ago or something when you first started organic chemistry, but we've taught you a lot of mechanisms. And I'm just telling you, for when you add alcohols and amines to acid chlorides or to anhydrides, you pull the base off second. These aren't, you know, triethylamine and pyridine are not super powerful bases like sodium amide. Okay, so now we're ready to push out this leaving group. There's those lone pairs just ready to do their thing. And they are pushing, 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 always pushing, pushing out. That's not a good looking arrow. Pushing out, there we go, acetate leaves, just like chloride leaves, same deal. So now we have this, this great leaving group here, and that's what generates our ester. Look at that beautiful carbonyl group. There's our bond to the ester, brand new. And we have a carboxylate leaving group in here. There we go. Acetate in this case would be the leaving group. Again, I circle my charges sometimes if I don't think I drew that so close to the oxygen. I'm just going to circle that so we know what that means there. Okay, so that's the mechanism for acylation of an alcohol or an amine by an anhydride. If it's an amine, you add first and then you deprotonate second, and that gets the leaving group ready to leave. Now, I want to talk about making bonds with carboxylic acids. Well, this is a lot trickier. That we have an easy transformation for taking carboxylic acids and substituting them to make esters, but we have to think about this carefully. You might think that, oh, if I want to attack the carbonyl, why don't I just use a super powerful nucleophile? Carboxylic acids are acids. If you take any super powerful nucleophile, like an alkylithium, or a Grignard reagent, or an acetylide anion, or an ethoxide anion, it's never going to add to the carbonyl, right? You may be thinking, oh, I'd like to add to the carbonyl. Let me just say that's not going to happen, because the first thing that's going to happen, the thing that is going to happen faster than anything, faster than forming any bond to carbon, is that you're going to transfer the proton. Protons are light. They have a mass of 1, the bonds vibrate quickly, they transfer quickly, everything's faster with a light atom like a proton. So you can't stop this acid-base reaction from occurring before any sort of nucleophilic addition reaction. This is always the first thing that's going to happen. And once you form the alkoxide here, it is over. If it was hard to add to an ester or to something as a lone pair, look, this lone pair is going to be donating so strongly into this carbonyl that nothing is going to add to that after that happens. So the problem is adding to carbonyls is slower, And deprotonating carboxylic acids by bases is always fast. So what's our trick? How are we ever going to get anything to add to this carbonyl, especially an oxygen nucleophile? And our trick is already, I've already mentioned this to you, is very simple. If we want to attack a carboxylic acid, especially with a weak nucleophile like an alcohol, we have to protonate that carbonyl first. We have to throw in an acid that is so strong that it can protonate the carbonyl, and that's how we're going to get alcohols to attack. We can't do it by adding a stronger and stronger nucleophile. We have to do it by making the electrophile more powerful. And so that's what we're going to do here. Let's go ahead and talk about the mechanism for making esters from alcohols and carboxylic acids by using strong acid catalysts. Well, I can't resist talking about acid chlorides first. This is I feel like I have to follow the order of the book. I'll get to that mechanism for making carboxylic acids into esters in just a minute. But we have to talk about this reaction that I already mentioned to you before when I gave you the list of reactions for this chapter. And that is how to make carboxylic acids into acid chlorides. And the conditions will look very similar to conditions that you learned about way back in the early part of the course for making alkyl chlorides. Not that interesting anymore because it's hard to do substitution on alkyl chlorides. When you made primary alcohols or secondary alcohols into alkyl chlorides, you use this combination of thionyl chloride and pyridine. And you use the pyridine in those reactions in order to soak up the HCl that's generated in the reaction. So that's nothing new. It seems like we're finally starting to talk about why we added pyridine to those reactions. And the SO leaves as SO2, sulfur dioxide, which is a gas. So this was the standard conditions. And to make a carboxylic acid into an acid chloride, we use the same reagent, thionyl chloride. Let me just draw that. I feel like it's worth drawing the reagent out, but you can just write SOCl2. It's pyramidal. There's a lone parent sulfur. You've probably never seen anybody draw the Lewis structure for thionyl chloride before, but that's SOCl2. I'm just getting kind of fancy here, writing out the chemical structure for you. And instead of adding pyridine, don't add pyridine to this. The pyridine would simply react with the carboxylic acid and you'd get the pyridinium carboxylate salt. And that's not what you want. What you do is you simply heat these. Don't write pyridine, that's wrong. So usually you put the carboxylic acid in benzene, add thionyl chloride, and you boil it. And you don't need a base for the HCl because the HCl comes out as this gas. If these reactions are working, as they're boiling along, you look at this little tube you stick on the top and you watch for this kind of white smoke coming out of the top. That's the HCl bubbling out, and you know your reaction is rolling along, and you can take off and go get some lunch and wait for your reaction to finish. These are good reactions forming acid chlorides. And boy, once you've got an acid chloride, you can do Friedel-Crafts acylation reactions. You can convert them into esters in high yield using an alcohol and pyridine. You can convert them into amides in high yield by throwing in an amine and triethylamine. It's so valuable to make acid chlorides. Now the book gives you a mechanism for this process. Ignore it, it's not the right mechanism. So I'm not going to ask you about it, and I don't want to confuse things. You don't need to know the mechanism for formation of, but it is a super important reaction. Okay, I took a little detour there. Let's come back and talk about the mechanism for getting alcohols to attack directly, on carboxylic acids. And I mentioned before, we've got to protonate the carbonyl. And we need powerful acids to protonate the carbonyl. Remember when we talked about making ketals and acetals by protonating the carbonyl in order to get alcohols to attack? We had to add toluene sulfonic acid, and you could have used sulfuric acid. In this case, we want inexpensive acids. This is not something where you're just going to measure out a few milligrams, a couple of crystals of toluene sulfonic acid. You're going to squirt in or like pour in, a couple milliliters of sulfuric acid into your reaction typically. And we're not that worried about measuring it out super carefully. So we use cheap acids. Could you use toluene sulfonic acid if you just didn't want to memorize HCl or sulfuric acid? Sure, I'd count that correct because the cost of the reagent is completely not an issue I ever asked. I don't think I ever asked you about that issue. So you could put toluene sulfonic acid. You just need something powerful here to protonate the carbonyl. These are equilibrium reactions. The catalyst doesn't change the equilibrium. all it does is make you reach equilibrium faster. And these are slow processes. 10 times more acid, 10 times faster. 100 times more acid means 100 times faster. That's the effect of concentration in these cases. So the only way to get the equilibrium to favor one side or the other is that we need to add excess. We've got to add an excess of the reagent in these reactions in order to get these reactions to work. So if you're going to use an excess in order to drive it towards the ester, it better be inexpensive. So really this is only a common reaction if you're using cheap alcohol solvents like methanol or ethanol. That's really, maybe in a few cases, isopropanol. That would be pretty unusual to make an isopropyl ester. Honestly, in the past 30 years, I can't remember anybody making an isopropyl ester because it's just easier to, you usually want to add things to carbonyls, and it's easier to do with methyl or ethyl than an isopropyl group. Okay, you have to use strong acids. And again, toluene sulfonic acid is okay, but you're not going to find examples like that in the book. That would be really unusual. So kind of expensive. Why would you, that's for if you just want a little bit, like you're making acetals. Okay, the conditions for this reaction, it's not easy. It's a slow process. It's not easy. Even when you throw in an acid, it's not easy. And even a powerful acid like catalytic sulfuric acid is powerful, but it's still a slow process because not very much of the carbonyl is getting protonated under these conditions, even though you're using a powerful acid. If we wanted to make an ethyl ester, we would use ethanol as the solvent. When I write ethanol or methanol below the arrow, that implies that it's the solvent and therefore it's present in excess. If you wrote the ethanol over here, that means one equivalent unless you write the word excess. If you write the ethanol on top of the arrow, that means one equivalent unless you say excess. So for these common ones, it's just common to dissolve your substrate in ethanol and then add in some sulfuric acid. Now, these reactions are too slow to be useful. And so I am going to I will demand that you write a symbol for heat. You boil it, you heat it up till the ethanol is boiling or the methanol is boiling. That's the standard way to run these reactions. And I want you to draw the delta symbol or write the word heat or do something to indicate that you have to heat these to get useful rates out of these reactions. If you just let it sit there at room temperature, you'd be waiting a long time, and I wouldn't consider that to be acceptable. So for this reaction where you take a carboxylic acid and an alcohol and you add catalytic acid like HCl or sulfuric acid, we refer to these as Fischer esterification. You know, this is German chemistry from back in the 1800s. I'm sure that these were introduced. It's kind of amazing they were doing organic chemistry back then. So these are, I will refer to these as Fischer esterifications. You've got to show heat for Fischer esterifications. Now, again, it's an equilibrium reaction. You've got to do something to drive that equilibrium. And one thing you can do is add an excess of alcohol. But in the case of cyclic substrates, there's no way to add an excess. And so you'll find that I often ask tricky questions where we're making 5-membered rings or 6-membered rings, and you may think, what a jerk, he's just trying to trick me. No, it turns out that reactions that make 5- and 6-membered rings just happen to work very well. And in this particular case, it's so easy to form 5- and 6-membered rings that you don't have to worry about this idea of excess reagents here because the two pieces are attached. They can't be present in more than a 1-to-1 ratio. So if I think about the substrate for this reaction, it might be hard to think about because you know you've got a carboxylic acid in the reaction and you know you need an alcohol in the reaction. And then suddenly, how do I think about it? This seems to confuse some people. Some people draw out separate atoms here, but you know if they're all attached in the product, then they were all attached in the starting material. And if you got confused about that connectivity, then just feel free to number things. Let's go ahead and number them just to make sure we got the connectivity correct. Here's a carbonyl group atom 1. Here's a CH2 group atom number 2. I see a carbonyl atom 1, a CH2 group number 2. I see a quaternary center number 3. There's quaternary center number 3. There's a CH2 group number 4 down here. There's a CH2 group number 4. I've got all the pieces right. So sometimes it helps you to enumerate your starting materials and your products, whether you're doing complex mechanisms with weird rearrangements, or trying to figure out how the pieces connect when you are trying to do a retrosynthesis, or try to figure out a multi-step strategy for making a product from a starting material. Sometimes enumeration of groups, CH2s to CH2s, CHs to CHs, will help you see what you need to do. Okay, so that's, again, you can't add an excess of the alcohol, but you don't need to when you're making 5- and 6-membered rings. Well, that's so much easier. And notice how I wrote the delta symbol on the bottom. If I ask you to draw the products, you don't need to draw the water, but I was asking you to draw the starting materials there in that box. Let's go ahead and talk about the mechanism for forming esters through a Fischer esterification, this acid-catalyzed esterification. I told you we're going to have to protonate the carbonyl, so let's get ready to do that. So for a Fischer esterification, you've got hydrochloric acid or sulfuric acid floating around in there. But there's a lot of protonated species. Some of that HCl is protonating the alcohol, some of it's protonating the carbonyl. We don't really care what the acidic species is. We just know that there's some sort of acidic species that's donating a proton to the carbonyl group. It's also protonating the alcohol, but I'm not going to draw that. That's not what explains the mechanism. It's happening. What I'm going to draw is the stuff that that leads to the product. Step 1 is getting the proton on the carbonyl. This is an equilibrium process. There's an A- floating around, and it'll pull the proton right back off. But again, we only care about going forward. So let's talk about the next step. Now that we've protonated that carbonyl, now we can talk about getting the carboxylic acid carbonyl group to react. I'll draw out a mechanism for esterification with methanol because that's easy for me to draw methanol, easier than ethanol. So just because it's smaller. And so now we've got this super reactive carbonyl group. I'll come in there and attack, and there we go. And then let's draw out the next intermediate for that process. Next intermediate, we've pushed the electrons up to this OH. It's no longer going to have a positive charge. That's going to be neutral now. And here's our nucleophile that just added in. And that now has a positive charge. It was neutral before. We formed a third bond. Now it has a positive charge. We refer to that as an oxonium ion, pretty common. And just like those cases I showed you before, we've got to pull that proton off in order to push out a leaving group. In this case, we're going to have to protonate one of the leaving groups. But let's just focus on deprotonation of this atom here. Now, if the conditions were basic, like pyridine or triethylamine, I would draw the symbol B. So I'm going to draw the symbol A- here because the conditions are acidic. It's acting as a base, but because the conditions are acidic, we use the conjugate base symbol for an acid, A-. So let's go ahead and pull that proton off. And that's going to lead us to this neutral tetrahedral intermediate. That used to be the carbonyl group. This other OH down below looks a lot like the protonated carbonyl. We can't distinguish these anymore. And now I've got my methoxy group. This was the nucleophile, CH3O. When we pull this proton off, up here, it regenerates an acid. There's the acid right there, just sitting there waiting. Now it's going to protonate. It could reprotonate the methoxy group. That's boring because that would take me backwards. I'm going to show the steps going forwards. Turns out these two hydroxy groups are indistinguishable, so I'm going to protonate the bottom one because it's easier to see that was substituted. There we go. And now that's a great leaving group. And now we're just totally set up here for some lone pair nearby to push out that leaving group. That's now an oxonium ion. I could use the lone pairs on oxygen methoxy group, but I'm going to use the lone pairs over here because that'll take me to something that looks more like a carbonyl. Wouldn't be wrong if I use the lone pairs on the oxygen, but you'll end up with this resonance structure and it would kind of add an extra step to your arrow pushing. So let me go ahead and acknowledge the fact that these protonated oxygens, like this oxonium ion here, is super easy to act as a leaving group. You did that earlier in the Chemistry 51C course, where you made T-butyl carbocations or tertiary carbocations by having water act as a leaving group. It's even better in this case because it's not just that water's leaving to form a carbeniamine with only 6 electrons. That water's getting pushed out. And we generate a cation that has 8 electrons on all the atoms, all the second row atoms. So that's exciting. It's nice to not generate carbocations with only 6 electrons. That kind of sucks. I'm smart enough to know here through experience that there's a proton I'm going to draw this bond here. That way it's easy for me to do arrow pushing with that. And then we have waters floating around now as a leaving group. So we have this protonated carbonyl. We also call that an oxonium, right? It's not named differently just because 2 of the bonds are part of a double bond. So if you were watching carefully, back over here in this step, we regenerated A-, so that A- counter ions floating around. And so now I'm going to draw it right over here next to this protonated carbonyl. And I'll draw the lone pairs. Fancy that. Now we just deprotonate here, pull that proton off, give the electrons back to the carbonyl, and we've got the ester. It's a 6-step mechanism. And it may seem like a long mechanism, but you need to know this mechanism, because the mechanism for forming esters under Fischer esterification conditions is the same mechanism as hydrolyzing esters using acids under acidic conditions. It's exactly the same intermediates if we hydrolyze an ester using water and catalytic acid, right? You just add an excess of water and it pushes the reaction back in the other direction, the equilibrium and catalytic acid. The only thing that changes is not the intermediates, it's the arrows. You just erase all the arrows, use the same intermediates, and then and make the mechanism go backwards. Okay, that's the mechanism for a Fischer esterification. Super important. Every single section of Chemistry 51C here at UC Irvine, or every organic chemistry course you take, they expect you to know that mechanism. It's really fundamental in organic chemistry. Okay, let's take a look at how to convert carboxylic acids to amides in one step. If I want to make esters in one step, I can, and I'm happy with methyl or ethyl esters, that's easy with that Fischer esterification. But what happens if I want to make an amide in one step? And I have the carboxylic acid and I have the amine. Here's the way to do that. You write the letters D, C, C. There we go. Boom. Done. That's it. It's that easy. But suppose I wanted to make an amide bond here. Well, you got to recognize which bond is the new bond. That's the bond of the carbonyl. That one. So if I wanted to synthesize this from any starting material on the planet, I would try to make that from an amide bond. But now that I know this DCC reagent, DCC, remember that DCC. Now I'm not breaking or forming that bond here to the sp3 carbon. So that better start off with the same chirality I ended up with. There we go. Right, that would be an R stereochemistry. So if it was R over here, better be R configuration over there in the starting materials. And the difference is, if I want to use this DCC, I need to have a carboxylic acid. So you need to learn how to use these reagents and think backwards. If I draw a box and I say, tell me what the starting material would be if you made this using DCC, you need to know how to figure out what the starting material would look like. So what is this DCC? It's a class of functional groups. It contains a functional group called a carbodiimide. Here's what a carbodiimide, and I drew the structure really small. You don't have to know the structure for a carbodiimide. It looks a little bit, carbodiimides look a little bit like carbon dioxide, except you have to put an extra functional group on the nitrogen. It's a condensation reaction, meaning you lose the elements of water, but you don't really lose water. The H2 and the O end up attached to the carbodiimide. You don't need to know the mechanism. Book doesn't tell you the mechanism. It's a long mechanism, and I don't think you need to know that. It's a great mechanism, very interesting, but we're not going to cover that. So if we're not covering the mechanism or talking about the structure of the carbodiimide, then all you need to know is DCC. The only thing is that just to remember that DCC is not equal to PCC. That's not, don't confuse pyridinium chlorochromate. If you write on your exam, oh yeah, I'm making an amide using PCC, I'm going to count it wrong. And if you say, oh, I just made a typo, I'm going to say, I don't care, that's wrong. DCC is a completely different reagent from the oxidant pyridinium chlorochromate. I wouldn't accept that, and that's completely, you're completely missing the point if you write PCC and you're trying to make an amide. Now, the book shows you one other way to make an amide. It's just completely crazy. My gosh, there's one case that I can think of where you would apply this. And what the book tells you is that, oh, you just take amines and you mix them with carboxylic acid and you get amides. It's not that easy, and it's super specific. This is a reaction that only works if you have no functional groups on R, if R is just alkyl. And it can't be a volatile alkyl, it has to be a long alkyl. There's so many exceptions to why this thing is not going to work for you. I would recommend you never use this reaction for making amides. The problem is that if you try to condense and release H2O from this, and you mix in amine with a carboxylic acid, you're not going to get any attack on the carbonyl. I already told you the first thing that happens when you add a base to a carboxylic acid. It deprotonates. So the first thing that happens is not attack of the lone pair on the nitrogen, it's deprotonating by attacking the proton. And once you have an O- on this carboxylic acid, you have a carboxylate, it's over because the lone pairs are going to be donating into the carbonyl, and it's hard to get any nucleophile to add to that carbonyl. The only way you can generate an amide is by taking the ammonium carboxylate salt that you generate when you mix them together and heating them at super high temperatures. Most organic functional stuff, bad stuff starts to happen when you thermalize compounds at extremely high temperatures. Just weird stuff. So you can't really have any functional groups on your R. It can be like long alkyl chains or something. The reason why they teach you this is how you make nylon, the polymer nylon, which has no functional groups. It's just two amines on a long carbon chain and two carboxylic acids on another long carbon chain, and you heat the heck out of them and you get nylon. Don't ever use this in my class as a way to make amides. If I ask you how to make nylon, you can say this is one way you could do it. Other than that, making nylon polymer, don't draw this out as a reaction for making amides. Okay, that's what we've got so far on the chemistry of carboxylic acid derivatives. We still have more cool stuff to talk about, such as saponification or soap making by cleaving esters to make carboxylic acids or carboxylate salts and alcohols. We'll be coming back to that on Monday. Go do a bunch of reactions. Go practice a bunch of reactions. Practice it on our online homework system. Practice the reactions in the book. Practice working mechanisms. Practice on our problem sets that we cover in discussion sections. Stay interactive with people that you meet during discussion sections, and just keep thinking about organic chemistry. I will see you guys on Monday.